Okay, so now I just wanted to do a problem that combines, again, energy and momentum, and maybe even forces too, right here. So what we have is we have a pendulum bob. I'm going to pull it back 90 degrees all the way up so it's horizontal, and give it I'm actually going to throw it and give it an initial speed of V naught right here. This thing's going to swing down right here, and down here I have another object right here. We could say it's a lump of clay or something sitting on a stand, and this thing's going to go down and it's going to stick to it right here, and now they're both stuck to this pendulum, and this pendulum keeps swinging, and it's going to just make it over the top right here. And so what we're given is, let's say we're given R, what do we want to find? Well, I'd like to find the speed when you're up here, V3, find V3. I'd like to also find the speed that these are going after the collision, which would be VB prime. So this is VB prime, this was V3. I'd also like to know what the speed is before the collision, which is VB. And I'd like to know what the speed that you threw it at, VA, is right here. I'd like to calculate all of those right there, given R right here. But I did say something else. I said it just makes it over the top right here, which means the rope right here just went slack right here. The tension in this rope, it's just going to go slack for that split second, and then it's going to fall, pick up speed, and become taut again right here. So the only force that's acting on it right there is the weight, mg. Well, the mass is actually m plus 2m because they're stuck together. So it's really 3mg right there. So you got 3mg going downward right there. And since that's the only force acting on it, we can look at the sum of the forces at that point. The sum of the forces inward at the top, since we're looking at the minimum speed, it's just 3mg. And since we're going in a circle, it's equal to mv squared over r. But the m is 3, so it's 3m v3 squared all over r. Okay, the 3m's cancel out. And now we've got the velocity at 3 right here. The velocity at 3 is equal to the square root of gr. Okay, you probably got that a few times already, and it's independent of how much mass it is. Okay, so we've got the first one. We've got the V3. So now what I'd like to do is find the velocity right after I want to work this thing backwards in time right here. Why? Because I was given that information right there. Well, between here to here, we can use energy because there was no energy. There was some energy loss in the collision, but then we're looking at after the collision. So all the energy right there is all kinetic right here because you're right at the ground right here. So we're going to look at, this is the energy. This is actually between B and 3. Actually, it's between B and 3. So the energy at this point, V prime maybe all I can say, right? The energy there is just all kinetic. So it's 1/2 3m times this speed squared, VB prime squared, and that should be equal to the energy at the highest point. The energy up there, it's got some kinetic, it's V3 squared, 1/2 3m V3 squared. And then you also have some potential energy too, because you're not down at the ground, you're at a height of 2 r's right here. So you got plus the mass, which is 3m g 2r right there. Okay, so from this equation, we know what V3 is. We can plug that into here. Now we can get VB prime. First, let's cancel the 3m's. Let's multiply by 2, so that becomes a 4. And so we're left with VB prime squared is equal to V3 squared, that's just GR, plus, what do we got over here? 4 GRs. 4 GR. So this is just 5 GR, just take the square root. So now we got VB prime, which is equal to the square root of 5 GR. So we've got VB prime. Okay. Now, if we work back, now we're in the collision process right here. When in collision, we always look at momentum just before and just afterwards. So now, if we write out our momentum equation for the collision, just before the collision, there was 2m moving at VB. That wasn't moving, so you just had 2m moving at VB. There's what we had. Then after the collision, you had 3m going at VB prime. So you had 3m going at VB prime. Well, we can get rid of the m's, and so VB is equal to 3/2 of VB prime, which is this, square root of 5 GR. Square root of 5 GR. So we've got that one right there. And now we just need to work our way back up to here. Oh, we're going to look at energy again right here. All of the kinetic right there must be kinetic and potential right there. So the energy between A and B now. So we'll look at the energy from A and B. At A, we've got kinetic, 1/2 mVA squared. Plus potential, we're a height R above the ground, mgr. And then at this point down here, we just have 1/2 mVB squared. 1/2 mVB squared. Let me come back one step right here. When I looked at the momentum equation up here, see that momentum equation? The 2m block, this one was only m. The 2m is over here, right there. So when this thing came in, the momentum before wasn't 2 mVB, it was just 1 mVB. So sorry, this thing should have just been 1 mVB, which means that this would have just been, if I had just divided that out, this thing would have been 3 VB. So there's not a half in there, so sorry. I didn't see that, that's just 3. Yeah, the VB, 2m is for this guy, not for that one. Okay, but that doesn't affect anything else right here. Okay, so now we said the energy here, which is the kinetic plus the potential. Down here, you just have kinetic, 1/2 m VB squared. Okay, we can get rid of all the m's again, right here. Multiply by 2. And we want to solve for VA, so from here, VA squared is equal to VB squared minus 2GR. We might as well plug this in down to here, so we get VA squared is equal to this squared, which is 9 times 5, which is 45 GRs. 45 GR minus 2 GR, which is 43 GRs, and then take the square root of both sides. So VA would be the square root of 43 GRs. Okay, so we've got all the speeds. The big hook in this problem was get this. I was telling you some information about that spot. It was the minimum speed. So that way I got V3, and once I know this speed and this height, I know its energy, and then I can set it equal to the energy there. And then with the collision, we looked at momentum, and then before the momentum, we looked at energy from here to here. I can't go from energy from here to here because there was some energy lost here. Now, I could have changed this a little bit. I could have made this an elastic collision right here, so that it came in and just bounced off of it. Remember, if you run into something bigger than you, this is going to bounce back right here. So I could have said, let's make this thing throw this thing, and so that when this thing came down, he didn't stick. He bounced back with a speed, say, I don't know what I should call that speed now, VC prime right here. And then this guy would go flying off, or he's just going to go flying off the end right there. And we could have said, how hard do I have to throw this down so when this thing recoils, it makes it right back over the top right there. We could have done that. Now you'll notice we would have had another unknown, because before we only had one speed after the collision. Now we have two speeds after the collision. And we would have needed another equation. But we could have used the relative speed equation right here. That would have given me the other equation. So the speed there would have been the same. It's independent of the mass. You would have still had this speed. Working your way back down to here, to just after the collision, we would have probably had the same speed there. And then in the collision process, you would have had two equations. You would have used the momentum and the relative speed right there, and then use the energy from here to here. So it's energy, and then in the collision use the momentum and the relative speed, and then back to energy all the way up to there, and then the sum of the forces at the highest point. Now this piece that got hit, he could have gone off a cliff, and then we could use projectile motion on that right here, you see? So we could just add all this stuff together if we want right here. Okay, so this will help you with, I think you might have had some homework ones like this.